Hey, welcome back. This is the chi-square test of independence walkthrough tutorial for how to do this in Excel. On the screen I have preloaded some of the example data we had from the lecture slide 6.2 where we talked about the student internships and if they helped a student confirm or not confirm if they wanted to work in that particular industry or not. Like before with the other Excel file, I have two tabs in this worksheet here. One of them is blank that we're going to be doing the walkthrough on, and the other one has a solution key that has everything we're about to do essentially filled out, and it's going to be made available to you. What you see on the screen here in the upper corner here is the observed. This is the data that we are starting with, and then we'll go through and do our calculations below. To the right of that is just some of our helper data that we're going to use to help get through these processes, and then a snapshot of the chi-square critical values from a chi-square critical value table. You'll notice this setup looks a little bit different when we do our observed versus expected calculations. Last time they were all in nice, neat little columns. This time it's sort of it's going to look like in a table form as we move down. This is because Excel, if we structure it in a column format, when we try to do the calculations to determine the p-value, it won't quite work out. This is the only way that we can get the accurate formulas to work out at the end instead of using it all in a column mode. So let's just go ahead and start out real quick. In the columns we have yes and no for if they did an internship or not, and in the rows we have it did not confirm, unsure, or did confirm if they wanted to work in that industry, and we have the data points from the slides. We also have the totals in the column totals and the row marginal totals along with our grand total. And so let's go ahead and start out. Are we going to need, up in G1 now, I'm looking to see, do we need the Yates continuity correction? Recall the Yates continuity correction is if we have 1 degree of freedom. So let's go ahead and figure out how many degrees of freedom we have. All right, 2 cells down, degrees of freedom, DF. With the test for independence, how did we calculate degrees of freedom? This is where we have the number of columns minus 1 multiplied by the number of rows minus 1. So let's go ahead and do an equal sign. How many columns do we have? 2, yes and no. So 2 minus 1 is 1, multiplied by how many rows did we have? 3 different levels of confirmation, so 3 minus 1 is 2. So 1 times 2 is 2. We have 2 degrees of freedom. Yates continuity correction says we need it if we have 1 degree of freedom, so we do not. We do not need the Yates continuity correction. And that is reflected in the rest of the formulas as we go down. If we did, we would have the extra steps where we take the absolute value of O minus E and then subtract 0.5. So let's go ahead and start with our process here. This is a little bit more work to find the expected values than we did in the goodness of fit. And what we need to do is we need to help make our lives a little easier. I am going to copy and paste my totals into the expected area. Whoops. There we go. Now, in order to find the expected value for those that did not have an internship and did not confirm if they want to work in that industry, start with an equal sign, open a parenthesis, and you're going to take the column marginal total of 17 and multiply that by the row marginal total for not confirmed, which is 13. Close the parenthesis, divided by the grand total, 33. And note, I'm clicking on the cell references. You can type in the numbers. Cell references make it a little bit easier. And our expected total here is 6.69 repeating, and that matches what we had in the slides. So I'm going to go ahead and repeat this process. Marginal total in the column times marginal total in the row, close the parentheses, divided by grand total. Marginal column in the multiplied by row marginal divided by grand total. Marginal times marginal divided by grand. Now, I could use a cell locking reference. That's when you have the dollar signs in front of the rows and or column names. And that could make it a little bit easier if we wanted to drag this formula around. But I'm not using that in this particular example. In some of those, this one I actually typed 33. Let me go back just for completion and use the cell reference. And so there we have the expected values in place. Now we need to go ahead and do the observed minus expecteds. So we're going to go ahead and do an equal sign, and we're going to go ahead and do 8, which is the observed for no internship and did not confirm, minus that 6.69 repeating, clicking on the cell references. And from here, I can let Excel do our work because it's going to be the same formula as we move it. Once I have that across, I can move that over there. And the same process for doing the squared values. Click on the reference point in that little table, square it, bring it over, bring it over. And then we're going to go ahead and divide by our expecteds. So we're going to take the value in our last step, go back up to the expected values portion and do a division. We are then going to drag it over, let Excel do the heavy lifting for us. And we now have all of the smaller parts of the calculations. We need to go ahead and collect the chi-square value itself. So I'm going up to cell G2 in my little helper area, and I'm going to do a sum function and add all of those values in that last step we just calculated. Well, that's not quite right. You know, I have a small error somewhere. That's the same. It looks like I accidentally clicked on the wrong cell. The nice thing about the cell references, if you just go back and correct your mistake, everything will update. And now we have the actual chi-square critical value that we had, the chi-square value obtained that we had from the analysis. I forgot to mention we are using alpha 0.05. You always want to set your alpha at the beginning of the analysis. Just reduces zeros there, make it look a little nicer. And now let's go ahead and find our chi-square critical value. What is it that we need to pair against? We're looking at the level of significance critical value chart in the 0.05 column when degrees of freedom equal 2. So I'm just going to go ahead and put a small shape on here to help it look easier. Degrees of freedom 2. Alpha is at 0.05. So here is our degree of freedom. I'm going to weight the outline a little bit more so you can see it more clearly in the video. Our critical value is 5.991. 5.991. And so is the chi-square statistic we obtained of about rounded 2.5 larger than our chi-square critical value of 5.99? No, it is not. So we are not statistically significant. I also had a little entry there for our p-value. If we want to calculate that out with a formula, we can use the equal sign CHISQ.DIST.RT function. It may start to pop up on the little help. You can arrow down, hit tab to fill it in. And remember, we need the chi-square critical value, comma, degrees of freedom. I'm going to go ahead and click on the cell references for these. Chi-square critical value, comma, degrees of freedom. And our p-value is 0.28 and additional values, which is much larger than our alpha value of 0.05. If you remember the speed limit analogy, the speed is going faster than our speed limit, and therefore we are not statistically significant. So we are confirming the same results we found with using the critical value. Remember, you only need one. Using the critical value or the p-value method, it's going to give you the same results either way. And just to kind of show you on the solutions key, we have all of the same values with information filled in to help you find this particular data. And there you go. I almost forgot, we want to give ourselves an effect size calculation here just for the tutorial purposes. Keep in mind, this was not statistically significant, so we're not going to be able to infer any effect sizes up to the population, but just for completion here, I went ahead and added an extra row in our helper areas for the effect size. Effect size is either going to be phi or Kramer's V, and that's going to be determined based on the size of our original table. Original table is 3 rows and 2 columns, which means we're going to be doing Kramer's V. Phi was only for a 2 by 2 table. So in order to figure that out, we're going to start with an equal sign. We take the square root SQRT function in Excel. SQRT, same as it is in R. Open a parentheses, and you're going to click on the cell that contains the chi-square critical value, divided by, and if you can nest this inside additional parentheses if you want, but otherwise order of operations should be fine. We need to then click on our grand total of 33, which is going to be multiplied by K min, where K is the smaller of the number of rows minus columns, minus 1. So we have 2 rows, 3 columns, 2 is the smaller, minus 1 is 2. And so we get, and I'll just type in here, Kramer's V. We have a Kramer's V of 0.275, which is reflective of what we had in other examples in PowerPoint. And there you go.